Hello, my name is Charles Wade. I'm a PhD student at the University of Colorado Boulder. This is a continuation of my series on example designs and kind of walking through how to use OpenVCAD to design multi-material volumetric objects. So today I'm going to show you another basic example that demonstrates how we use convolution. So if we go ahead and open up the example directory that's provided with OpenVCAD and go under Basic and Convolution Example, and open that up, we're going to see this script. So if I go ahead and render this, you can see we're going to get this kind of object with 4 discrete material areas and blending across each one of them. So if we zoom in, you can see, each one, the cyan and the red, we get blending, cyan yellow individually, and then 4-way blending in the direct center. So the way that we achieve this is using what we call convolution, right? So it's very similar to image process convolution, but it's actually being performed in 3 dimensions over the material distributions. So when convolving an object like this, we're going to be looking at 100% material distributions of each one of these, so 100% red, 100% cyan, at each one of these, right? And then at the boundaries, we want to be able to convolve or sort of mix, in this case, across them. And the way that we do that is with this convolve node. So starting from the inside out, you can see we defined 4 different prisms or rectangular prisms. We've translated them to each one of these 4 quadrants and made them a different color, so red, blue, yellow, cyan. Now we want to perform that convolution across them, right? So actually, I'm going to go ahead and delete the convolution just to show you what it looked like. If we render this, we get these 4 specific discrete material boundaries, right? So bring in the convolution back. The way this convolve node works is it takes some kind of user-defined kernel. For specifics on exactly how this works, I recommend you go watch the video I did in this playlist for the OpenVCAD presentation, and I have a nice visual that walks you through this. But just know that this is very similar to 2D image kernels, where we kind of have a matrix, or in this case, a 3D grid, because we're convolving over 3D space. The way we define this is in a sort of Python-like way, where each one of these numbers, right, is actually a value in this bigger grid, right? So, each number is surrounded by square brackets, and then each row has a set of square brackets, and then finally, every single one on top of that has another set of square brackets, right? So this really defines a 3D grid, right? So this is in this case a 10 by 10 by 1 kernel, right? If we wanted one more dimension, let's say we wanted to make it 10 by 10 by 2, we would add an extra value inside each one of these inner arrays, right? But in this case, we're going to be looking, 10 voxels above us, 10 voxels below us, and remember that a voxel is defined, by this value up here in the root node, so this has an impact on exactly how this convolve, or rather what these ranges get correlated to. So in this case, that would be 10 times 0.04, or it would look 0.4 millimeters on each side of one of these boundaries. And then it just applies the convolution on top of that. So when we sample it, every given place we sample for this visualization is going to be convolved, right? So if I look at this in the ray tracer and we convolve this, you can see, we get these discrete material regions, and this is in full 3D, right? So if I turn off yellow here and we peer kind of inside the actual visualization, you can see we have these material regions that are fully 3D. It's not the same on every single layer, right? And we could perform these convolutions in that extra looking dimension when we're doing the convolve if we wanted to make it like that. So one other example I'll show with convolution is convolving these 2 spheres. So in this case, we have a 9 by 9 by 9 kernel, right? So this does get a little laborious to define in script. I recommend, if you're doing this a lot, to maybe write something that helps you generate this. But if we go ahead and visualize this, to It's going to take a while. Convolution, in this case, a 9 by 9 by 9 operation, is a fairly complex operation on the tree, and as such, it's going to take a while to visualize. So I'll come back when it's done. Okay, so I went ahead and let that load, and you can see now we've performed a convolution of these two spheres. Right, you saw we had one sphere defined here, we defined another one in red, and translated a little bit to the left. That would be kind of looking at it from this direction. I just turned the camera so we can see it with the light. Now, one of the cool things we can do is actually peer inside this to look at how the convolution is being performed in 3 dimensions, right? So you can see here, we're kind of blending across this, right? We've extended this blue, it's kind of exploded a bit to the right. Likewise, if we look at the red by transitioning out the blue, we can see that same sort of effect happening over next to it.